So the next session is about commonly used techniques to fabricate a scale model. What we'll do here in this session, we'll set an appropriate file format for a slicer software to define a pathway of 3D printing to finish a model. First, what we need to do, first we will open a appropriate CAD software. What we'll be using here today is a SolidWorks software for CAD modeling. Sorry. This is the software. Here we have a standard specimen for tensile testing according to ISO 527-2 for extrusion plastics. We have this model here, which is in part format, which is used in SolidWorks software. On this following picture, I'm showing you the dimensions of sample used for tensile testing. Here you see that the length of a whole specimen is 170 millimeters, that the width of a specimen is 20, and these here parts to the left and the right side are gripped in the tensile testing machine, and from this here curve to the next one you have the open area, and the only dimension vital for tensile testing is this which I'm showing you now, which is 50 millimeters. That's where we see the breaking of the specimen, and that's the only area we are about to consider. On the next picture you can see the thickness of the specimen, which is 4 millimeters. This how here in this CAD software we extrude a sketch to a model. I'll close this window now. So you see the specimen here. Now what we will do is to save this file in appropriate format. So this is a specimen for testing appropriate to ISO 527-2. Now I'm saving this part in STL file format and saving it to desktop. What it does is that it uses a CAD model to triangulate it. In this file format you make many triangles on the outer surface, and that's how you make a model here. In this particular case we have 92 triangles. Now, okay, and we have this file saved on desktop right here. This is our specimen. So available technologies for this here session are FDM, fuse deposition modeling, and SLA. In fuse deposition modeling we are deposing a thermoplastic material on a built platform in layer by layer manner. The next technology is SLA for polymerizing a liquid plastic. The techniques are similar but different, and I'll show you in Slicer software how they differ in preparing of the model. The first what we shall use will be a FDM technology, and this is the Simplify 3D is a appropriate software for preparing a model for printing using FDM technology. This is the window of the Simplify 3D software. It is a licensed software, so only if you buy it you can use it. There is another type of software called Cura, which is an open source software. Here you see the cards, file, edit, view, mesh, repair tools, which are used for preparing the model. First, what we will use, just focus on the upper window. We will import the model. So we've saved it on desktop. That's the location. I'm clicking on it, and now I'm opening it. So it just popped in on a build platform, and you can see that it was imported. The upper window shows how many models are you importing for the printing session. In the lower window, here is a type of process which will be used for 3D printing, and on the whole screen you see a build platform. It is already set for appropriate device. Our 3D printer has a build platform of dimensions of 400 by 400 by 400 millimeters. So we have a decently big build platform. So I've already inserted a model in here, as you can see it, but I don't like the orientation of printing. So I will click on it, double click on it, and you can see here that I can scale the model by changing the scale. So I've inserted a model, as I told you, with a largest length of 170 and largest width of 20 millimeters. I can reset the scale, or I can change it. So if I am so here I can enhance the dimensions. I can make it bigger or make it smaller using these percent values. I can change the specimen width, the specimen length, sorry, to 200, for example. And by using uniform scaling, if I press enter, all the other dimensions will change appropriate to this here dimension. I can maybe unclick the uniform scaling, so the dimension I will change will be the only one changed. If I set the uniform scaling, it will be scaled according to the specimen geometry. I can reset the scale, and the values will go back to 100%. So it will go to the original value. Now I can change the rotation of the specimen. I can rotate the specimen. So you see here the axis, X, Y, and Z, and this is the first coordinate point. So I will rotate a model for 90 degrees, click enter, and now the largest surface is on the build platform. The next thing what I'll do is that I will center and arrange. I'm now centering the model. So it is placed here. I want maybe to rotate it again using double click again, and we are about to rotate the model to 90 degrees according to z-axis, and now it's done. We'll center the model again, and now we have the model on build platform. The next thing what we shall do is that we will duplicate this here model, because we need 5 specimens for the ISO 527-2 tensile testing. I'll use simple commands, ctrl plus C and ctrl plus V. Now I've duplicated the first one. I'm selecting both models, duplicating them again, and I'll just duplicate only one. Now we have 5 specimens. I'll center models again, select them. I can select them on build platform, or I can select them in this upper window. So by using a next cursor, one below, I will move the models on the build platform. I can move them anywhere I like, and for this here session we'll use the location closer to the starting point, which would be right about here. Now we have all 5 models placed where we want them to be printed, and the next thing what we need to do is to set a process of printing that is in this here lower window. So we already have one process set, and that one we shall edit for our 3D printing. So by clicking the edit setting, it is editing this here process 1 and showing us in the window on all these cards the parameters for particular printing. So first we can name the process. So for example, I'll type specimen ISO 527-2. We can select a printing device. Maybe we have many, or just one in our case. So we are clicking on German Reprep X400 dual extruder. Our 3D printer has 2 extruding nozzles. After that we are setting a material. This here program has a predefined values for 3D printing of PLA and ABS, and because we are using we have 2 extrusion nozzles, we can combine materials, PLA and ABS, ABS and PLA, just moving the printing nozzle, that one on the left, that one on the right, and the other case around. Or we can use PLA with PVA. This is a neat material for PLA because it can dissolve. And with ABS you have HIPS material, which can dissolve in limonene type of chemical. With PLA material, PVA can dissolve in water. So you print with 2 materials using PVA for support, maybe, or not, and just place the model in the water or limonene, and the PVA or HIPS will dissolve, leaving only PLA and ABS. The next parameter asks us to auto-configure a printing quality. So it already has some defined values if we want to print fast, or if we want to print in high detail. I'll choose medium for this case. On the next card it asks us whether we shall print on the left extruder only, on right, or we would use both extruders for printing. I'll leave only the left one for this here example. Then the infill percentage, asking us the percent of infill of this model. I'll show what it means in the following minutes. Does it include Raft or generate support? These are the parameters we shall see in a minute or two. So in the first card we have options for extruder. Using left or right one, we have PLA material in our left extruder. What is the index of our tool head? The nozzle diameter. It's a hole in our nozzle. This is the value of width of material extruded from the nozzle. We have 0.4 millimeter nozzles on the extruder installed right now. You may have 0.2 for more detailed 3D printing, but if you want to print in more detail, it will last longer, so the optimal nozzle diameter is at 0.4. On the next card, it asks us the rate of extrusion, which is 1 to 1, then the extrusion width, and now the ooze control. We can define a retraction of the filament and speed of retraction and so on. What retraction means? It's when material is extruded, the rollers push just a little back material, just push it, it pushes back the material just for that particular case when you expect oozing of material. You don't want extra dropping on the printed model, which will cause failure. So these are the standard values for PLA material. For retraction distance, extra retraction distance is that extra move of a roller in extruder to just push back the material again. The retraction speed of all the process, and now coasting and wipe distance. It shows us here when will the printing of one layer end. So from these values here, we see that the printing path would end at 0.2 millimeters, close to the end, and the wipe distance is that the last 5 millimeters of path will be just wiping from the nozzle. Not that these 5 millimeters would have any extrusion, just that at that point, 5 millimeters before the ending of the path, it would just stop and wipe the material from the nozzle, ending a perfect layer. Now the next card here asks us about layer settings. This here technology prints in layer by layer manner, so the thickness of the layer is a primary parameter to set. This here printer can print in 0.3 millimeter, 0.2, and the highest resolution is at 0.1 millimeter. We'll set 0.2. So now it asks us about top layers, how many we have to define a number of top solid layers, bottom solid layers, and number of outlines. Top solid layers and bottom solid layers show how many of the fully printed layers there are on the top and on the bottom side of the model. In between top and bottom layers, there are layers printed with certain infill pattern with lower material percentage wrapped around outlines. So in this here particular case, we have 4 top solid layers and 4 on the bottom side and 3 outlines. So I'm skipping to a infill card. Here we define a pattern of infill, which can be rectilinear, grid, triangle, or wiggle, and mostly used honeycomb, full and fast. I'll select a fast one. External fill pattern, which can be rectilinear and concentric, leave it at rectilinear, and percentage of infill set at 75. So I'll show you what it all means. I'm preparing a print, and this is how a printing looks like. This is a first layer on the bottom side, fully printed. 1, 2, 3, 4 layers. Next we have layers with infill pattern, covered in outlines. 1, 2, 3. Look at the blue lines. Those are outlines. And as we go layer by layer, we come to the top layers. 1, 2, 3, 4. This is a concentric pattern of layers. I'll choose rectilinear to show you how it looks like. Okay. Now I'm preparing a print. This is a rectilinear pattern. So returning back to edit process, and now to show you the next option in layer card, that's first layer settings. First layer is the one that should be tightly gripped to build platform. How well the adhesion to the build platform is of the first layer, that shows you how well a model would be fixed to build platform. So a first layer always has to be more tightly pressed to a build platform. So here I have 90% of layer height of a first layer and 120% of the width of the first layer, comparing to a original layer. And I've set that the printing speed of the first layer is half the speed of the any other layer. This is how you set a first layer parameters. Then let's look at the additions. We usually use skirts or brims, how they call it, and rafts. First I'll show you what is the skirt in this occasion. I've set one layer of skirt and with just one outline with offset of 3 millimeters. So when a printing starts, you have that risk that a material from the nozzle won't start extruding the plastic at the first time. So you are making a one line around a model just to make sure that after it would print a model with continuous flow of the plastic through nozzle. So that's how a skirt looks like. It's just a one line on one layer, 3 millimeters from the raft. And now let's show you what a raft is. This is where we define it at additions. These are the raft options. Here I've chosen 2 raft top layers with 100% of material in those layers and one base layer with 3 mm offset from part. The first layer we have here, which needs to have a better contact with build platform, is a first raft layer. This is a base one. So the next layer is a top one, first top one, and now the second. Why do we use a raft? It is considered best to print such a structure for better gripping of a model during print. So this is how a raft looks like, and upon the raft we build a model. Let's return back, and another parameter to consider is the separation distance, a distance between the top layer of the raft and the first layer of the model. I have set it here to 0.2. We have a layer height of 0.2, so I think it's fairly decent. Now we have a support as an option. So when a part of a material needs scales to be printed, we use this support structure just to hold a model for construction of layers that are overhanging. I'll show you. I'll import another model to show you what I mean. So I will use these card holders as an example. I'll rotate them around y-axis, this one too, this one as well, and center and arrange. So as you see here, I'll prepare a print. So we have these support structures. So when it is building a model, now going up, it builds this support structure for this layer now, for this layer to be well printed. If there were no support structure, this layer would just fall down. And this is the only way to print this kind of model I've imported recently. So on support card we define a support parameters. I've defined here that support is at 25% of material. So it would print one layer, one line, then skip 3 and print another one. That's what 25% of support structure means. Extra inflation distance, that's a distance between a top layer of support and the first layer of material supported by this structure. Then you have, maybe you can use dense support layers. I'll choose one just to show you how it looks like. So the dense layer is the last one preceding a model. So this is the dense one if you need better dimensional accuracy of a model. So now you're certain that the model would be decently printed. Now let's get back to process settings. Next card is temperature. Here we set a temperature of extruder and heated bed. The temperature of the extruder is a temperature of liquid plastic extruded from a nozzle. For PLA, 200 degrees Celsius is considered as best value for printing. Then temperature of heated bed is set at 60 degrees Celsius. Higher temperature of heated bed is there for better gripping of a modeled to build platform. So underneath build platform here you have heaters to generate these 60 degrees Celsius. We'll get back to another card. Now it's cooling. For certain materials, you're advised to cool your model after a certain number of layers. For PLA, you don't need to do that. The next card is about GCode. Well, here you define your 3D printer, its limits in build volume, the values of your build volume. And another thing to consider here is baud rate. When you are connecting your 3D printing machine to your laptop, be sure that baud rate of your laptop, which you set here, and a baud rate value on your 3D printer match. This is really a parameter to consider. Next, script. If you want to make scripts and nodes. Now speed. Here you define a general value of printing speed, which is set here at 40 millimeters per second. Next few options are under speeds when performing outline, infill, support structure, which is set at 80%. Next, we have other. Bridging, that is when a nozzle is skipping from one part to the other. That's the movement when nozzle is not extruding a plastic. So when you have a material that is over extruding, this is a parameter to consider. Next, you have filament properties. Here you set diameter of your filament, price of your filament, and filament density for this software to calculate how much material you will use in this printing session. Then you have advanced options. Ooze control, when material is over extruding. You have some plastics which just extrude more than the others, and this is a parameter really to consider in that cases. Then modifications in layers. You can print with one process setting in this here window. You have to start at 0 millimeters, of course, and here you set a stop value at like 5 millimeters or such, and then in the next process setting you are starting at a stop value of previous process till the next stop, and you can continue till the last layer of your printing model. So I'll uncheck these fields. So that's about it for the basics. Now we have a prepared factory file with process settings. How we save this job: we go to File and we save factory file as. I'll send it to desktop. And so now we have a factory file. Next, we'll prepare models for print. This is how a printing will look like. We can preview this by line using toolhead. Now I'll show you how this works. I'll play. This is how it makes a skirt, then raft. Now this is finishing the first layer. This will be a while, so I'll fast rewind it. And this is a complete path of our toolhead during the process. Now it makes support structure. As I told you, set on 25%. You see, that's about it. And now it finishes a model. That's it. I'll uncheck toolhead and preview by layer. This is all previously shown, and that's our GCode here. So we have a calculation of build time and how many filament we'll use for this process, weight of plastic, and material cost. How we save this is a GCode file. What we see here is interface, but we are generating a GCode based on the previous factory file. So we can print over USB or save it to disk. It's all the same. And I'm saving it as a GCode. So I'll save it on my desktop. And that's it. And we have it right about here. Sorry. Now this is a factory file, so this is a GCode file. I'll open it using a notepad. If you had any lessons about GCode, this is one of the kind. So we have in first lines we have all the parameters we have set in factory file, and from this line on we have a pathway for our stepper motors to finish a printing of our models. These lines look endless to me, so I'll just fast forward them, and that's it. And build summary of build time. Everything I've shown you in the software interface is contained here in this note, and that is what this note is what 3D printer is using for building a model. Alright, next, this was a preparation of model for FDM software. Now for the other 3D printer, which is based on SLA technology, a particular 3D printing device is called Form 2. It is of a Formlabs manufacturer. It uses a preform software. It is much easier to use than the previous one. So this is at the beginning you have this window asking you of of the connectivity of your printer and which resin shall you use. So we'll set this at gray. We'll choose a gray resin material. In the fold down menu, you can choose between various types of resin for SLA printing. You have standard ones for casting, a ceramic-like material, clear color, some biocompatible resins for dental use, some mechanical resins as well, durable, flexible, high temperature, a model one for building dental models, rigid, tough, and white. So we'll stick to the gray one. The version of material we have is V4, that is the latest one. And then we are about to define the layer thickness. So in the previous FDM technology, our highest layer resolution was 0.1 millimeters. Here in this technology, this is the lowest resolution, and we can choose between 0.1, 0.05 and 0.025 millimeter, which is the highest resolution for this particular technology. We'll stick to 0.05. It gives decent models. You can't notice layers in the model. That's how well the models are printed with 50 micron resolution. We'll apply these settings. So we have an interface of build platform. We have a front side and wiper side. So we already have a orientation of build platform. Size of build platform is 150 by 150 by 150 millimeters. So it is sufficiently smaller volume than the FDM 3D printer we have. We have in this here interface cards for basic manipulating on the upper left corner. On the left side we have printing buttons, and the lower bar shows what we have chosen for a particular session. We see that we've defined a 3D printer we use, resin material, and layer thickness, and we are about to see a volume of our new print and how many layers we need to make for this session, and print time. We'll see that in a moment. So first we'll open files. I'll import a specimen we will print on FDM. So this is a model in STL. On the left side, first upper button is size, scaling. We'll leave it at original value. The next button here gives us an option to finish printing quickly. So the software would generate a print by itself. If not, we have these three buttons for us to perform preparation of a model. So the first button is orientation of a model. I can orient it by clicking these buttons and using this here ball with rotating rings. So I'll lower a model a bit. Sorry. Now That's it. The next button, generates supports, will create a touch point size of 0.6 millimeters. That's a point of support which touches the model, and it will be with 0.6 millimeter thickness. We'll generate supports. We see here that for this printing we need 10 millimeters of material, milliliters of material, and for performing a 3D printing we'll use 2289 layers. A printer still generates supports, and the far right option shows us a printability of our model. Are the supports good? Is there any issues? Would there be any troubles printing? So on and so forth. And the print time is about 7 hours with this here option. So soon it will show us a is the model printable or not. It is. Let's see. So there are no stress concentrators or cups in this model. Cups are is a probability of vacuum in any of the model when you're printing cups or something, and when a build platform soaks in the material, and you may trap air inside, and by pulling up the platform maybe it would result in breaking of the material from the structure because of the generated vacuum. So we'll place it here. We'll add those card holders. I'll choose one card holder just for an example. Again, I'll do the orientation. I'll rotate it a bit. So next I'll generate support on it as well. Alright. So this one card holder has a crack in it. It's a model of compact tension specimen. And that's it. Model is ready for printing, and the next thing we do is that we click on Start Print button. We have a job name, and when we connect our PC to the machine, we click on Upload Job button, and we are we click on Upload Job button, but still we don't have a PC connected to 3D printer, so I will go to File menu, close this window, go to File menu and save this job as Specimen ISO 527-2 with a card holder. So the format of the job file is form. I'm saving the file on desktop. As we see, the printing volume is about 60 milliliters with 2372 layers and about 10 hours of printing. So on desktop we now have both files for printing, one for FDM as a GCode file and one for SLA as a form file. Those files need to be uploaded on each 3D printer to start printing, and we'll see in the next session how the models will look like. So thank you for your attention.